bioinformatics micromodules using dynamic programming to perform local alignment. In this module, we discuss local alignment, which means we only align the middle parts of the sequences. In the previous modules, we have talked about global alignment, which aligns the whole sequences. So why do we want to perform local alignment sometimes? The reason is that for a lot of sequences that are parts that are important for their functions, if these parts are mutated, the functions can be disrupted, and therefore they are usually highly conserved. But there are also other parts that only play a supporting role. The sequences of these parts can be mutated more freely. So even for two sequences with the same function, if we use the whole sequences to do the alignment, they may appear to be not so similar. So it would be a good idea to align only the parts that are similar. However, in a lot of cases, if we do not know a lot about the biology of these sequences, we do not know exactly the parts that we should align. So the idea of local alignment is that we try out all the middle parts of the sequences we want to align, and then we report the one with the highest alignment score. Now let us formally define this local alignment problem. The inputs for the pairwise case again involve two sequences, R of length m and S of length n. What we try to do is to find the alignment or the alignments, if there are multiple of them, that aligns a subsequence of R and a subsequence of S and has the highest score among all possible subsequence pairs and all possible ways to align these subsequences. Here, the differences between the local alignment and the global alignment definitions are highlighted in red. The keyword here is subsequence, which means the middle part of a sequence by cutting out some characters at the beginning and some characters at the end. In the extreme, we could cut nothing, that means the whole sequence, or we could cut everything, that means the empty string. After finding out those alignments, of course, we also want to output the corresponding highest alignment score. Now, to illustrate the ideas, let us consider a very simple scoring scheme in which we have +1 for a match and -1 for a mismatch or indel in the alignment. This is an example that we previously used to illustrate the global alignment ideas. We have already found that if we do global alignment, the optimal score is 3, and there are 3 different ways to get this optimal score. If we look at these alignments, we see that there are actually parts that are not so well aligned. For example, if we look at the first alignment, the first column is a match, which is okay, but the second column is an indel, and the third column is a mismatch. So now if we are allowed to cut out some of the characters from the beginning or from the end, why don't we cut out these 3 characters? If we do that, then we get an alignment with alignment score 4. In fact, in this case, that is the optimal local alignment. In this example, it also shows that we can specify the local alignment using their positions, because there could be multiple occurrences of the alignment part, GCGT. So here, we use exactly the starting and ending locations to indicate where it occurs. So GCGT actually occurs from position 3 to 6 in sequence R and from 4 to 7 in sequence S. Now, how can we find out the optimal alignment and optimal alignment score? Again, we want to use dynamic programming. We again define the table V, where Vij equals the optimal alignment score of some subproblems. In this case, each entry in the V table does not correspond to only one subproblem, but rather a set of subproblems. To illustrate the idea, let us use this very simple example. Suppose we are aligning ACG with AGG. For the cell that we are pointing at right now, For the global alignment case, it means the best alignment score between CG and AGG. How do we know it's CG and AGG? Because it is for the suffix starting at that position for R, which is CG, and the suffix starting at that position for S, which is AGG. In the case of local alignment, actually, we not only consider this one single subproblem, but also other subproblems that are formed by taking the prefix of these two suffixes. For example, we can have CG with AGG, CG with AG by cutting out the last character G, CG with A by cutting out the two Gs, CG with an empty string, C with AGG, and so on. There are many different subproblems. So this one single cell actually compares all these subproblems. For each one, we get the optimal score, and then we compare all these scores and put down only the one with the highest number. So this sounds to be a much more difficult problem than global alignment. Can we easily use dynamic programming to solve it? The answer is, surprisingly, yes. And the difference between the algorithm for global alignment and local alignment are very small. The algorithm is called Smith-Waterman algorithm, which is named after the two inventors of this algorithm. In the initialization stage, on the last row and last column, instead of filling in 0 and then -1, -2, and so on, we only fill in 0. The reason is that if there's a negative alignment score, that part of alignment is actually a burden to the overall alignment. Now we are allowed to cut out some of the characters at the end. Then why do we still need to keep those parts? We can simply say we cut out those parts, and correspondingly, we have a 0 for those parts. And in terms of the recursive formula, actually the form is very similar to the global alignment case. The only change is that if the final number after comparing the three directions is a negative number, we instead put down a 0 there. Finally, after filling in the values of the whole table, we want to look for not the upper left corner anymore, but the number that is the highest in the whole table, and that would be the optimal alignment score. Again, that is because we can cut out some characters at the beginning of the sequences, so we do not need to always look at the upper left corner. This is an example. So we are not going to fill in the numbers together. You can take that as an exercise by yourself. What we want to see here is that if we look at the whole table, the highest number is 4, and therefore the alignment score is 4, which is what we already know, because the best way to align these two sequences is to align the GCGT in R and GCGT in S, and the score will be 4. Starting from that 4, we can do traceback. In this case, it's very simple. It's always diagonal path. So the optimal alignment is exactly the GCGT from R from position 3 to 6 aligning to the GCGT from position 4 to 7 in S. We are going to talk more about the traceback because there are more details to that. However, before that, we want to know why this algorithm actually works. It seems that the problem is very complicated. Why making only those small changes can turn the algorithm from solving global alignment to solving local alignment? In order to answer this question, we want to use several cells in this table to explain. First of all, for this entry that I'm pointing at right now, for this 0, by definition, the meaning of this number is the maximum of the optimal alignment scores of 6 different alignments. The first one is to align R5.6 with S6.6. Second one is R5.6 with an empty string. The third one is R5.5 with S6.6, and so on. For each one, we want to compute the optimal alignment score, and then we take the maximum of the 6. That is the definition of this 0. And similarly, we can write down the definition of this number, which is the maximum of 2 numbers. This one is the maximum of 3. This one is the maximum of 4. Now we have defined many different values. What we try to do is we want to rewrite the numbers in the first box using the numbers in the other boxes. The way to do that is, for example, for A, actually it is the maximum of the three possibilities, namely the diagonal path together with a mismatch because we want to put the G and T in the same column, or the horizontal path introducing an indel, or the vertical path introducing an indel. So if we look at the numbers, actually it is exactly the maximum of G together with the mismatch penalty, I together with the indel penalty, and L together with the indel penalty. Similarly, we can rewrite the other terms using the numbers defined in the other tables. Now with this, we can rewrite the maximum of these 6 terms by rearranging the terms. Finally, we see the formula is exactly the maximum of V6A-1, V5A-1, and V67-1, and 0. That is exactly the formula we had in the previous slide. So that is an illustration to show that this algorithm is exactly solving the local alignment problem. Now it is time for us to study the traceback mechanism. Again, we have highlighted the differences between the local case and the global case using the red color. The first difference is that we want to start with the cell with the highest score. Sometimes there are multiple of them. Then we're going to start from each of them one by one. The second difference is that we do not always need to go all the way to the lower right corner. Anytime we reach a 0, we stop there and then we output an alignment. If there is still one or more incoming edges to this cell, we can continue to form other alignments, as we are going to show in an example later. And finally, when do we stop the whole thing? For each path, if we reach a cell with no incoming red arrows, then of course we cannot go any further and we stop there. So this is a complete example to show these ideas. We're trying to align AC-AGC with AC-TAG. Notice that in this case, we have changed the scoring scheme a little bit. For indel, it is -2 rather than -1. If we look at this table, we see that the largest value is 2, and there are 2 different occurrences of them. Namely, the first one is on the upper left corner, and the other one is on the 3rd row and the 4th column. Now, if we want to trace back, let's say we start with the one on the upper left corner. We go there, and then follow the red arrows backward. In this case, it's very simple. It's only diagonal path. So we go 2 steps all the way to the cell with a 0. Since we reach a 0 here, we can stop and output an alignment. That is exactly the first alignment we show at the bottom, which is aligning AC at position 1 and 2 of R with the AC position 1 and 2 of S. For this cell, we see that there is still an incoming red arrow, so we can actually continue the trace back to go horizontal, which introduce a gap to the sequence R, and then we have 2 more diagonal edges. So in that case, we form the second alignment, involving the sequences from position 1 to 4 in R and position 1 to 5 in S. With that, we finish the traceback for the first occurrence of 2. Now we can start at the second occurrence of 2. So if we do that, we start from this cell, and then we have 2 diagonal arrows. So again, we can form the alignment, which is the third one here, aligning the positions 3 to 4 of R with the position 4 and 5 of S. That is the last alignment, and we have finished the whole traceback process. Finally, let us compare the alignments for global alignment and local alignment. If we look at the 2 dynamic programming tables, we see that for some entries, they have the same value, but in general, the values in the local alignment case can be larger than the global alignment case.